Hello, and welcome back to the Cedille cast. This video is the start of a multi-part sequence covering the generic derivation of induction for efficient Mendler-style lambda encodings in Cedille. This development comes from a recently published paper in the Conference on Interactive Theorem Proving. A link to an archived version of the paper and refactored codebase is given in the video description. This video will cover some background material needed. That is, we'll cover the subjects of functors, algebras, initial algebras, and Mendler-style algebras. It is well known already that data types can be represented as the least fixed points of their signature functors. That is to say, a functor formed by a sum of products based on the data type's constructors, with recursive occurrences of the data type in constructor arguments replaced by the functor parameter. For example, the data type nat and list can be given the following signature functors. So first, we will import some useful definitions: the unit type, dependent pairs, and coproducts. Nat, the signature functor for nat, can be defined as the sum of unit representing 0 or r representing the successor of some other number. Data types with parameters such as list can take that additional parameter as an extra type argument. Lists are defined as the sum of unit representing nil and a pair whose first component is the head of the list in some list formed by cons, and whose second component is the tail of the list, with the placeholder r representing this. We saw something like this already in the previous video, deriving Tarski's theorem for least fixed points of monotonic functors over a complete lattice. However, the fixed point we will derive for these functors in this video is different. It will be the carrier of their initial algebras. The usual definition of an algebra over some functor f, i.e. an f algebra, is defined as follows. Algebra is a type family over a functor and a carrier. It is a function from f of x to x. That is, for some functor f and a result type x, called the carrier of the algebra, alg fx is a function that takes some f of x and computes a result by combining subresults. Here is a simple example of this: a function computing whether a given nat is even, phrased as an algebra over natf. Is even alg is an algebra over the nat functor computing bool. Since natf is defined as a sum, we will use the elimination rule for sum called case. When we are in the left case, corresponding to the number being 0, we reply that 0 is even. In the successor case, if our predecessor was even, then this number is odd, and vice versa. So we provide not. An initial F-algebra is intuitively the best or a most general algebra, one which has a special relationship with every other F-algebra. With imperdicative quantification, we can define the carrier of the initial algebra, and thus the initial algebra itself, in a very concise manner. This carrier of the initial algebra is the representation of an inductive data type. Given some functor f for all x, given any algebra, f algebra over x, results in an x. Operationally, the definition of fix says that it is the type of functions that, for any f and carrier x, it can satisfy the requirements of any f algebra to produce a result of the carrier type. The special relationship between initial F algebras, the initial F algebra, and every other F algebra is the existence of a unique fold function, categorically called a catamorphism. This fold function is a generalization of fold over lists, and in Cedille it is defined as a function that takes any algebra and produces a map between fix f and the carrier of that algebra. Our D of type fix f has this type for all x given an F algebra over x produce an x. We have a particular algebra in mind. Thus the result of this expression, the type of this expression, is x. Continuing with the example above, we may define is even over nat, where nat is the fix of natf, as a fold of the is even algebra defined here. Everything covered so far is fairly well known, with perhaps the imperdicative encoding of fix being less familiar than the more usual definition of a functor fixed point in terms of an inductive definition. To begin pivoting towards new concepts, let us first observe that the definition of nat as fix natf has a big drawback. Similar to the church encoding of numbers, computing the predecessor for these numbers takes linear time, because the algebras are defined in terms of previously computed results, rather than in terms of the direct subdata of a number. An alternative model of data types is as the carrier of initial Mendler-style algebras. Mendler-style algebras are different from the usual algebras in that they allow access to the subdata directly through an abstract type. Given a functor f and a carrier x, a Mendler-style algebra is a polymorphic function quantifying over some type r, given an r to x function an f of r and returning an x. You can view this quantified type r as the type of data for which it is legal to make recursive calls on. The algebra is equipped explicitly with a function to make such recursive calls of type r to x. If we read this type signature parametrically, the algebra is given some unfolded data, f of r, and the only type correct thing that it can do with this is to apply its recursive function of type r to x on these r subterms. The carrier of the initial Mendler-style algebra is defined similarly to the above. Let us use the same is-even example with Mendler algebras to demonstrate the difference. Given an abstract type, r, a function for making recursive calls on, and some unfolded data, we will case analyze our unfolded natural number. In the 0 case, as before, we reply that 0 is even. In the successor case, just making it easier to see. In the successor case, we have direct access to the predecessor n prime of n, but only at this abstract type r. We make a recursive call on this, and then invoke not on the result. The fold of Mendler-style F algebras is defined similarly. As well as the definition of is-even itself. We conclude this video by making a start on some generic definitions. The fixed point rolling and unrolling function for any functor f. Viewers familiar with recursive types will note that so far we have made no appeals to monotonicity, that is, to the positivity or covariance of our functors, instead letting them be arbitrary type schemes. Positivity is needed to find out the unrolling function. The next video will provide the tools to finish the definitions in terms of the ID type, which, similar to the cast type we saw in previous videos, is a type of zero-cost coercion that can be used to define a notion of positivity. Our generic rolling function in takes some f of fix mf and produces a fix mf. For Mendler-style algebras, it is definable for an arbitrary type scheme. type we must inhabit, fixmf, is a polymorphic function type. For all x, given an F algebra with x as the carrier, produce an expression of type x. We have available in the context an algebra This algebra is a polymorphic function whose quantified type R represents the type of recursive occurrences of subdata in some unrolled data f of R. Here we may choose what the type of R, how to instantiate the type variable R. This we will instantiate it with fixmf. We must now produce a function of type fixmf to x, but we know how to produce such functions already. So the recursive function that the algebra is given is the folding of the algebra. Finally, the last argument must be a term of type f of fixmf, which we have by assumption. As stated before, the out function is not so easily defined without additional assumptions of the type scheme f. Here, to finish the definition, we will use the more familiar notion of a functor. As being a type scheme that comes equipped with additional mapping from any two types a to b, lifting a function from a to b to a function from f of a to f of b. Here we must produce an expression of the unfolded type f of fixmf. D lets us compute the result of any F algebra. The result of any F algebra, the carrier of any F algebra, given some F algebra. So we will invoke it here and insist that this be f of fixmf. So now we must produce an F algebra whose carrier is f of fixmf. where R is the abstract type of recursive occurrences in the unfold data. Rec is the function by which we explicitly make recursive calls, and FR, the unfolding of the data type D. We have available in our context FR of type f of R, and a function rec for making recursive calls. We need to use fmap in order to map rec over fr. Given some little r of type R, we invoke rec on R to produce a result of f of fix mf, and then we can use the in defined above to produce a result of fix mf. This approach, requiring that our type scheme f is a functor, including that it requires the functor laws, can also be used to generically derive induction for data types. The approach we will use will instead require the existence of a zero-cost cast between the abstract type R and fix mf, and a mapping function which lifts this coercion over f. We will define these concepts and use them to augment our definition of a Mendler-style algebra in the next video. Thanks for watching, and hope to see you then.